Alright guys, today we're doing a little bit of work with scientific notation. First we're going to talk about what exactly is scientific notation. Well, first off, it's just another way of writing a number. So you can rewrite numbers in this fashion. Now, you could write any number in this fashion, but it's specifically good for very, very, very large and very, very, very small numbers, okay? But the big key is that you aren't changing the number when you write it in scientific notation, you're just writing it in a different way, okay? It'd be the equivalent of writing 100 versus 100. These are the same number. One is using numbers and one is using words. Now, this isn't scientific notation. What scientific notation does is it takes the advantage of the unique properties of 10 and multiplying and dividing by 10. So first, really quickly, just as a simple review, I want you to think of what happens to a number always when you multiply it by 10 and what happens to a number always when you divide it by 10. Pause and think about it if you need to. So when you multiply by 10, all it does is it moves the decimal place one spot to the right. And it may add a 0 onto the end too. If you said adds a 0 onto the end, you're right for many numbers, but not all. Like think about the number 1.9. If you multiply that by 10, you get 19. You're not really adding a 0 onto the end. Okay, so you're moving that decimal place one to the right, and if there's nowhere to move it right, like with the number 19, if we were to move that decimal place one to the right, well, there's nothing there. We still put it there, and we fill in our blank with 0 then. Then that's correct. And likewise, when we divide, we move the decimal place one to the left. Okay, scientific notation takes advantage of that fact. It also takes advantage of exponents, knowing that if you multiply a number by 10 to the 5th, you're really just multiplying by 10 5 times. Okay, so scientific notation looks like this: A times 10 to the B. That's what all scientific notation numbers look like. A number times 10 to an exponent. The key is A has to be less than 10 and A has to be greater than or equal to 1. Okay, so A cannot be 10. That first number can't be 10. That first number's got to be between 1 and 10. It can be 1, but it can't be 10. Okay, so it's like a single digit number. Now there can be decimal places after it, but it's like a single digit number with a decimal place or a few after it. Okay, that number B needs to be an integer, so a positive or negative whole number. Okay, an example would be 3.72 times 10 to the 15th. That would be scientific notation. The first number is between 1 and 10, and the exponent is a whole number. Okay? So what we're going to do is figure out all the different cool stuff we can do with scientific notation. There is some very cool stuff we can do with it. We'll start with the easy stuff first. How do we know specifically what number we're working with? Because you see a number in scientific notation, you may not be able to interpret it in the exact same way that you did numbers in regular old decimal form. So let's take 3.75 and let's go times 10 to the 7th. Okay, if we wanted to convert this into decimal form, we just need to understand what multiplying by 10 to the 7th means. It means we're multiplying by 10 7 times. Okay, and every time you multiply by 10, that decimal place moves one to the right. So we take 3.75, we move our decimal place 1, 2, 3, 4, 5, 6, 7 places to the right. Now, when we see those gaps, we have to think, okay, once we multiplied by 10 twice and hit 375, if we multiplied by another 10, we wouldn't really be just moving it to the right, we'd be moving it to the right and adding a 0. So we'll fill in zeros. And there's our number. Now, if you want to stick some commas in there, you probably should, just so you can read the number a little bit better. This looks like 37,500,000. Okay, so you can see why this might be useful for really large numbers. Okay, because if your original number was 3,280,000,000, writing out all those zeros would be silly when you could shorten it way up and skip all the zeros and write a decimal number times 10 to an exponent. It's also good for really small numbers. Okay, so let's do 3.75 times 10 to the negative 7th. What we know about negative exponents is it's the same thing as 1 over the positive exponent. So really what we're doing here is we're dividing by 10 7 times. Okay, so if we divide this number by 10 7 times, that decimal places go in the other direction. 1, 2, 3, 4, 5, 6, 7 times. Put the decimal place there and then go ahead and fill in zeros. Okay, so we get a really small number. Okay, we got that 375 with 6 zeros before it. Crazy small number. Okay, so that's how you convert back to decimal form. Okay, or your standard form for numbers. A decimal form to scientific. So let's say we wanted to write a number in scientific notation. So let's say we had the number 375,000. Yep, I'm pretty much using that 375 over and over again. So here's what you need to do. You first need to figure out where would I put the decimal place in this number. Where would I want it to be? It's right here right now. Where would I want it to be if I wanted it to be a number between 1 and 10? Well, I would change it to 3.75. 0.375 is too small. 37.5 is too big. So it's got to go between the 3 and the 7. Then I figure out how many times I would need to multiply or divide by 10 to get back to my original number. Well, if my decimal place is here, 1, 2, 3, 4, 5, I would need to multiply by 10 5 times to get back to my original number. It works the same way with decimals. So let's say we had 0.0375. I would again want the decimal between the 3 and the 7. And if the decimal place is between the 3 and the 7, I would need to divide by 10 twice to get back to my original number. So that's times 10 to the negative 2. Hopefully that's fairly straightforward for most of you. I can certainly help you out a little more if that wasn't clear. But the really cool thing, really awesome thing about scientific notation is being able to multiply and divide really large numbers without necessarily needing to even use a calculator. Okay, so let me show you two really cool examples here. Okay, actually I'm going to show you three. Two basic ones and then a tricky one. 4 times 10 to the 15th times 2 times 10 to the 30th. These are both really huge numbers, maybe numbers that you're using in a science class, like when talking about distances in space or masses of planets. And you need to multiply these numbers to figure something out. We can use our normal exponent rules to figure this out, because remember, you're allowed to this is all multiplication. 4 times 10 to the 15th times 2 times 10 to the 30th. So if we reordered our multiplication, we could reorder the multiplication and put 4 times 2 first and get 8. And then we can multiply 10 to the 15th times 10 to the 30th together. That's multiplying powers with the same base. We just add the exponents and we get 10 to the 45th. We're done. This is a valid answer. Our answer's in scientific notation. Our original numbers were in scientific notation. We're fine. That's great. It's a good answer. We don't need to write out 45 zeros. That's just silly. Okay? That's why scientific notation is really awesome, because it gives us the power to multiply those really big numbers together. Let's try another one, except this time let's do division. Let's go 8 times 10 to the 5th over 4 times 10 to the 20. Okay, again, we can simplify this one at a time. 8 over 4 is 2. 10 to the 5th divided by 10 to the 20th, subtract your exponents, we get 10 to the negative 15th. We got a really, really, really small number as an answer, which makes sense because we took a big number divided by a number that was, well, much bigger than it. There's only one place where this gets a little bit tricky. Obviously, if you have numbers that you or decimals or things like that that you can't multiply in your head, you may need a calculator to help you out a little bit, although not entirely too much. But here's where it could get a little complicated. Let's say we had 5 times 10 to the 10 times 3 times 10 to the 11. We multiply together just like the last one, and we get 15 times 10 to the 21. Technically, this is a correct answer, but you should always be putting your answer either in standard form or in scientific notation. This is neither, because our original number here is too big. Our decimal place is here. We don't want it to be there. Okay? So what you have to do is figure out how to get this into scientific notation. You work it pretty much the same way. I want the decimal place to be between the 1 and the 5. Okay? What that means is I now need to put an extra 10 on the other side to balance things out. Or let's think of it this way. What I did is I divided this portion of the number by 10. I divided 15 by 10 to make it 1.5. I can't just divide that number by 10 without also multiplying it by 10 to balance things out. So I divided the left portion of the number by 10, and I multiplied the other portion by 10. It's like a balancing act. I had to drop this side, the left side, by 1 decimal place, which means I had to up the other side by 1 decimal place. Okay? The other way you could think about it is this would be a 15 followed by 21 zeros. I would have to, so that means 1.5 moving at 22 places would get me those 21 zeros that I would need after 15, because I'd move it 1 to get back to the 15 and then 21 more to get the 21 zeros. Okay, so that's the only trick that you have to watch out for a little bit, is you may need to adjust your number to make it in scientific notation. Sorry for the long video. Hopefully it was pretty straightforward. If you have questions, talk to me, put them in your WSQ. Definitely try some practice problems on this.